In this part, I will be covering bundle shape similarity analysis in BUAN. In BUAN, we perform bundle shape analysis with bundle adjacency metric. Let B1 and B2 be two bundles, where bundle 1 is shown with green streamlines and bundle 2 with red streamlines. We'll say that small b1, which is a streamline that belongs to capital B1 bundle, this one, this streamline is adjacent to B2 bundle if there is at least one streamline in B2 that has MDF distance with B1 streamline less than certain threshold. So for example, let's see this streamline. If this streamline and this streamline, we take the MDF distance between these two streamlines, and if it's less than certain threshold, then we will say that they are adjacent to each other. So this really depends on threshold. If threshold is very low, we would say they are not adjacent. And if it's very threshold is higher value, it's more lenient, even this streamline could pass for being adjacent to this streamline. The coverage of B1 by B2 is the fraction of B1 that is adjacent to B2. Coverage ranges between 0 when all streamlines in B1 are too far from B2, and 1 when every streamline in B1 is adjacent to B2. So for example, when all of these streamlines are adjacent to the red streamlines, we would say the coverage is 1, and if they are all far from B2, then we will say the coverage is 0. The symmetric measure bundle adjacency is the average of coverage by B2 by B1 and the coverage of B1 by B2 as shown in this equation. Now let's see how we can use this bundle adjacency metric to perform shape analysis. We create a tree-like structure from our data. Here we can see we have a parent bundle P, and then we create a child bundle from this parent bundle, which is the exact replica of this bundle. We call it C1. Then we create another bundle C2, that is the child bundle of P, which has some area here missing from the parent bundle or its sibling. Then we create another child, that is C3, which has a different part missing, the upper part. So this one is this lower part here. Then we create C4, which doesn't have this fanning part of the parent bundle. And then the last child or node, C5, which is just the middle part of the parent bundle. And now we demonstrate how we can use bundle adjacency to do shape analysis. So as we saw earlier that the threshold plays a main role. So let's set a threshold of 5, which is a low threshold. This is 5 millimeters. So if BA, bundle adjacency, from now on I'll call it BA. If it's within this threshold, the threshold that is used in that equation is 5, then it means it's almost same, 1. And here, since there are few streamlines that are not in here, or this is not exactly the same as its parent, so we give it the bundle adjacency score or shape similarity score 0.826. And in the case of child 1, C1, because these are the replicas, so we say it's the same. And as we move to the right, we have C3, which is again missing some part of the parent bundle, so we give it 0.766. But still it has the shape is same, but it's not exactly the shape same because it's missing some streamlines or the density is different. And as we move to right to C4, here we come to see the shape is very much different because we don't have the end parts of the bundle. So we give it the score of 0.237. And for the C5, since the shape is not similar at all, this is just the middle part, and we don't have that kind of a C kind of a shape, so we give it 0 because the threshold here is very strict. Now let's see with a different threshold. When we increase the threshold to 15, which is more lenient. Now in the case of C1, we can see that because these are exact same replicas, it should always be 1. And here again, this is lenient, so it says that although the number of streamlines is different, this is more dense as compared to the C2, but still the shape, overall shape is very much similar. So it gives us this 1. 1 means that there are the highest shape similarity between two bundles, and 0 means no shape similarity at all. So here in C3, again, the overall shape is same, maybe a bit difference at this part here as compared to the C2. So we give it 0.9 at 7 with threshold 15. And to the C4, again, it's not exactly the same, but the shape is kind of same. So we give it 0.88. And this is interesting when we go to the C5, which is, if we look at it, it's not, the shape is not same, but this is child of this P, parent. It means that this is part of this bundle. There is some part that is the same. So it should give it some similarity score. So here with the threshold of 15, we are giving it 0.543. So this truly depends on user, what they want, how strict they want shape similarity to be. If very strict, they can go to 5 or even less than that. Or if they want to see just there is some shape similarity or some parts that are similar, then they go to a higher threshold like 15. Here we show that how we can use this bundle shape similarity score to create bundle shape networks. On the left we have 5 subjects, and this is a fully connected network or a graph where each node is connected with every other node, and in the nodes are the bundles, and on the edges we have shape similarity score. So here we can see different score among different subjects. On the right side we have shape similarity metric, because it could be difficult when we have higher number of subjects to visually see the graph, so we have the metrics here. And in the diagonal it is 1 because it's shape similarity calculated with itself. And here the legend is from white to blue. White means lower shape similarity and darker blue means higher shape similarity, that is 1 in the diagonal. And here we can also see most of them have somewhere around 0.8. In some cases, for example, subject 3, subject 3, which would be this one, with subject 2. Here we can see that there are differences between these two. So as relatively it has lower shape similarity from other subjects. So there is an overview of bundle shape similarity. So here we have patient data in red, and in green we have control data. So this here in previous, as we saw, we had those bundle segments and bundle profiles. Here we don't provide that information, we don't need that. Here we just give the extracted bundles from auto-calibrated breaker bundles in common space. And then we give it to the shape similarity method, which creates these shape similarity plots. This result is shown on PPMI data for 64 subjects, 32 control, 32 patients. So the first 32 are control, and the second 32 subjects are that belong to patient data. Here we have calculated shape similarity between one subject with every other subject. And we can now finally see exactly what this pixel means, what value is there. So if we look here, that we have these are the two bundles, and this is the score between those two bundles. This is very useful because this kind of metric could also be used for quality assurance, as I will explain later. And this is the example of all 30 bundles that we have in the BUAN paper, and shape similarity among all 64 subjects. And here, as we look at this, if we just look at it, if it's darker, as we can see from the legend, it's the same. If it's white, it means less shape similarity, and if it's blue, it's darker blue, it has a higher shape similarity. So if we just visually look at it, we can see there are some bundles that are very dark. The metric for shape similarity metric is very dark. For example, uncinate fasciculus right, even left, MLF, left right, ML, even forceps minor. On average, most of them are blue. And here we set the threshold to 5 millimeters, which is a strict threshold. So this kind of serves as a quality assurance measure, where we can see for how many subjects we were able to extract the bundle, how good was the bundle extraction, or how good is the data, or is there any problem with some subjects, is there any trend that for some subjects we cannot find certain bundles. For example, here if we look at arcuate fasciculus right, there are many subjects that don't have arcuate fasciculus, or if they have, it's very thin, it's not very dense. That's why it's more, here we see a lot of white lines, or yeah. And also from the literature, we see that many people are left heavy. The left hemisphere is heavy for the arcuate fasciculus, and the right is not that heavy, or we don't find arcuate fasciculus right in many subjects. And if we look at this MLF right, here there is one subject that just doesn't have higher shape similarity score, and all others have higher shape similarity scores relatively. So we can say that this one subject doesn't have this bundle, or there is some problem with this one subject, with this bundle, this string. And also for optic radiation, here we can see OPTL, we can see here is the optic radiation. So it also has one kind of outlier. So we can also use this to find outliers in the data, or even if they are not outliers, maybe there is just one bundle that we cannot find, or there are some problems with it. Another interesting thing that we can do with this data, or we did here, is we did hierarchical clustering of shape similarity matrices. Here we can see this is arcuate fasciculus left on left, and arcuate fasciculus right on right, and we did some clustering here. And here these bars tells us that green means control and red means patient. So this tells us which group it belongs to, that subject, because now the order is changed. Before we knew that the first 32 were control and last 32 were patients. And here we can see some clusters, and especially on the right we can see there are like these clusters here that are created from the different subjects. So for example, here we have this one cluster where we see the subjects that have less shape similarity are more white. We couldn't find many bundle there, or many streamlines there. They are clustered together. So we can say these are some subjects for whom we couldn't find arcuate fasciculus right, or if we could those were very thin. And here maybe this cluster has darker shape similarity, so we could find Archaeophysiculus here, or they fall in the same group. So we can see from here what are the clusters. So for the left, overall it has maybe this one cluster here and then bigger one here. So some of the practical uses of BUAN, the uses are in the multiple domains of science, engineering, and medicines. For example, a psychologist who wants to develop a theory about the brain's function, they can use BUAN. A neurologist who wants to find which brain pathways of a patient have defects or they deviate from the normal population, they can use BUAN. Or a neurosurgeon who wants to see the longitudinal effects in patients after tumor surgery or any other brain surgery. An engineer who develops new ML algorithms, they can use the data generated from BUAN or even the method itself and make changes to it, maybe extend it. A data scientist who wants to find patterns in the data and extend the proposed approach. A network scientist that wants to understand the connectivity of the brain, or a medical student who wants to learn the major pathways of the brain or investigate the possibility of new pathways. An MR physicist or a radiologist who wants to automatically quality control the MRI data coming out of the scanner. And one more thing that I want to mention is BUAN is very generic, and here we have showed it with the human data, but it could be shown, we can use it for animal data, given we have the atlas for the animal data, and we don't need to change anything in BUAN. I'll stop here, and in the next part, we'll see a live demo of BUAN.